a little bit more exact. Yep. Can I get a volunteer, please? On the board or the topic? So, that's touching the board? Yeah, that's straight. All right, so 2.67 meters, thank you. And so let's predict the wavelength. We'll see how close we get to what the manufacturer says the wavelength is. And so my wavelength is going to be dy over Ln, just 0.000175 meters, times y, which is 0.0395 meters, divided by L, which was 2.67, times n, which was 4. Double check, make sure I had. Yeah.
Got a 6.47 times 10 to the negative 7th. Meters here.
Sounds pretty good.
Pardon?
That sounds pretty good.
It does. And the manufacturer
I think it was
Like
6.5.
is somewhere around 650. They give a range.
Yeah.
They say anywhere from 635 to 670.
Yeah.
Okay.
So, some validity in what I've been telling you.
You haven't just been pulling it out of the hat.
That's right. So it's been a dream to actually see how long I could go in a class just making up outlandish stuff and see how long.
Just waving your hands, smoking mirrors.
That's right. You know, I've gotten away, not on purpose, but I misspoken in class and no one's questioned it. Part of me is thinking, if I could go an entire class and no one ever questions it, that really doesn't bode well.
No, that just means we trust what you say.
Yeah.
I'm not sure.
Yeah.
Or, yeah, I'm also afraid that I'm gonna say something outlandish and then on test someone's gonna say, but in class you said, and then quote me exactly what I said. Missing the part where I said all of that was made up. And the other dream is to give a test, like in the movie Exam.
I've never heard of that movie.
Psychological thriller.
Oh.
12 people in a room, all vying for the same job. And they have 80 minutes, something like that, to answer the question.
Oh.
But they have to figure out what the question is first. And then there's some violence that I'd have to do it without the violence. All right, any questions about the double slit or the grading, the diffraction grading? Oh, let me actually show diffraction grading. That was the other bit. Cornell plate fortunately has diffraction grading on it. And I put the diffraction, here, I'll put it over here.
Yeah, I'm pretty sure if you tried that exam thing on me, you might get the infinite monkey. You might get the infinite monkey. You'll get a bunch. I might just answer with a bunch of gibberish.
Well, also part of the movie was that only one person was gonna get the job. So, I guess only one person gets the A, but.
I think that make for a good psychological experiment.
All right, so hopefully you can see, we don't have to turn the lights out, but you can see that the lights are brighter than they were before.
Yeah.
And far more distinct. Because again, you have more than one more than one slit where the light's going through, all sort of compiling on each other.
Yeah, it looks like the bright spots were turned into dots. That's what it looks like from my.
Oh, yeah, in essence, yes. You probably get more, if we turn the light out, let's see how.
Yep.
There's a little bit more of a spread with the light out, you can see a little bit more of the spread, but not much, it is pretty much dotted as opposed to the distribution. Okay, lights. Oh, no.
I was just trying to see what what the diffusion grading looks like, but, only time class.
Well, this one, if you look closely enough, and I'm assuming if I can see it, anyone can see it. If you look closely enough, you can see a bunch of, I'm in the middle column here, you can see a bunch of little lines.
Yeah, I can see them, I'll let, better pass it out.
Yeah. This one, you really can't see the lines. This is also a diffraction gradient right here. That is 13,400 grooves per inch.
Oh, wow. Can I see that laser pen?
That's Einstein.
What's with this one right here that, I guess that simulates a hair? There's like a slot that kind of gets wider, and then there's a
Oh,
line between.
yeah, I've never really used that one. That, so you can do single slit or double slit,
Oh, okay, that makes sense.
but since you don't have specs on it, demonstration purposes,
And these
this
are-
is the 500, this is roughly the same as that, I think. This is 530 grooves per millimeter.
Does this thing work?
It just makes it,
It probably does.
That's just,
you can't really tell, it's just blurry.
yeah. Oh, here's the. Yeah, this is, I think that's the same as that one.
This one's
that's-
less blurry.
Is it, okay.
Yeah.
Oh, I see how this thing works. You look at it through, with your eye, you don't shine a laser through it.
Well, we would shine a laser through it in order to actually do experiments, but you do have, I guess you're basically doing diffraction grading. That's what happens when white light shines through it.
Sort of like a prism.
Yeah, in some sense. The physics behind it is different. In a prism, light travels different wavelengths of light travel different speeds through the same medium. And in this one, you've got physical interference.
Oh, gotcha.
Or then you can see many rainbows when looking on the light.
That is awesome.
You see rainbows.
Yep.
It gets organized and then disorganized, and then at some point it'll become organized again.
Yeah, I tried shining the laser through it to see if it would do anything. It didn't look like it did anything.
It did not?
It just looked.
Good.
Yeah, that's what I got. It just looked like a dot.
Yeah, turn the lights out. Oh, okay, sure.
Let's see what it does now.
I keep using,
Yeah, there we go.
Really spread out.
yeah, it spreads out a whole lot more, because the second dot is way over there. Let's see, oh, 2 dots, sometimes you can see a third dot, or n is equal to 2. I don't really see it at the moment.
Something that I've always asked.
Is it off? Yeah, I'm not seeing beyond the first NX one.
All this stuff leaves me questions, like, what does this stuff, what would you use things like this for, such as the, double slit, the way.
I found a research on the internet that they find a structure of the DNA through this diffraction gradient. They signing a gamma X-ray through a DNA, and they found the structure look like the X.
Oh, okay.
Yes, and they found out the structure is a look like a spring.
And there's a whole lot
That's what I
of
know. Applications.
interference patterns, which are like the crystalline structures. You shine light in it, you see how the interference, look at the interference pattern. So you get thicknesses of, you know, like bubbles, you get thicknesses of bubbles based upon the interference patterns that show up.
Oh, okay.
And then also the structure of DNA.
Yes.
So it would help with really small, very imperceptible.
Like in
phenomena.
And also, the interference patterns that we're discussing here also apply to electrons, and so you look at electron interference patterns in other cases. All right. Questions on the double slit and or gradient? All right, so let's talk about the hair experiment and sort of correct myself, some of the issues I had.
And you said that was a single slit experiment.
That was a single slit. No, the hair was a single slit, and so, let's make sure I get, Babinette's principle. Stuff that's not in your book. Actually, I don't think your book does single slit. All right, so, I'm gonna sort of quote what I've written down here, which I think comes from Wikipedia, but I've seen it other places, they probably are all quoting Wikipedia. I'm pretty sure this was not wording from Wikipedia. All right, so if I have an opaque obstacle, in other words, the hair, and it's clear around it, so basically I have hair and I got open space around it. It gives the same diffraction pattern as if it were opaque everywhere around it, but clear where the hair was. So basically, we're flipping where the light can go through. Now, the reasoning is this, if I shine a light at a target, I'm gonna get some distribution of light. This light scatters, depends on how narrow this is, depends on if it's a laser or whether it's just a light bulb. But I have some light I'm shining on it. This light reflects the amount of energy that is in the light itself. And then I put an obstacle in there. Oh, actually, if I put an obstacle in there, that means I'm suddenly gonna, I have light that's gonna bend around it, so I'm gonna start to get a diffraction pattern. And so I put an obstacle in there, I get a diffraction pattern, and what we saw in class last time was we had a really bright spot here, and then a dark spot, and then that's too much there, it's much dimmer than that. We get a pattern like this. If that's the case, we draw that one. So if I flipped it around, if instead of having one opaque thing here where light can't get through, I then reversed it so that that's only where light can get through, whatever pattern I get should just be that plus the sum of the, plus this should get me this. Because that's all the energy there. This is all the energy with nothing blocking it. This was blocking only just a small piece of it, and then if I flipped it around, this would be whatever's left over. So here, all the energy that gets through here. The previous scenario, all the energy got through except for what was here. Yes?
So what we see in the middle would be a more accurate version of that, distribution pattern over there.
I'm not quite sure the wording works out. Let's see if can we do it slightly differently.
That's just what I was thinking.
If all the energy looks like that. So I shine a light onto a surface and I get light bouncing off of it, and I somehow measure the energy coming off.
Oh, okay.
That would be the sum of that. I keep making it as big as that one is, I don't want to. Plus whatever the difference between those two is.
Oh.
So this is not quite as big as that is, so I've got, and that's,
I was trying to Google Babbitt's principle,
yeah, I'm not sure I can draw this right.
just to.
Yeah, I'm drawing it wrong. Basically, if the whole is 5 and one of them produces 3, I know what's missing is 2. So if that's the whole thing, and this is what one of the scenarios produces, the other scenario must produce that for the whole.
Oh, okay.
Now, more accurately, and part of the reason why I was having difficulty there is if that's the whole thing, and then I do a single slit experiment, and this is 7, then what's missing is -2. Because one of the patterns is producing something larger than that, and the other one is producing the negative. Now, why does the negative look like the same as the positive? Because it's just an amplitude. Ultimately, it's an electric field and a magnetic field playing with each other. And our lights and our eyes sense a positive amplitude the same as a negative amplitude. It's only 0. Closer it is to 0, the duller the light is. And so one of the patterns will be positive, the other one's negative, but we can't tell the difference from looking at it. That's what Babinet's principle is. And so when I had the single hair there, that was single slit diffraction. Or it should produce the same pattern as single slit diffraction. That was the justification that I ignored last time, just called it double slit. So ultimately what you see in brightness is you have a bright spot here, dark spot, bright spot, and so forth. And then within that, we do have double slit interference going on. So this would be the single slit envelope. And within that, you have the double slit pattern. And so when we did the measurements, I should have used the single slit formula. So our numbers last time were a little bit off. But this does, of course, and I know what you're thinking. You're going, yeah, it's the single slit formula, but what is the single slit formula? I'm glad you asked. The single slit formula. The big difference between the double slit and the single slit formulas is double slit formula tells you where the bright spots are, the single slit formula tells you where the dark spots are. So let's go back to Huygens and his idea of waves. If you have a wavefront here, so this is the crest of a wave, he viewed every single point along here as basically basically a seed for the next wave. So that this one produces a wave, that produces a wave, that produces a wave. And so you add them all together and it ends up looking like that. But each point produces a wave. So if I have a single slit, I can think about this as a whole bunch of new points from which a wave will be produced. So that if I take this point, so if I'm looking at my screen over here, and I take some point over here, those are supposed to be straight. Call that R1 and R2. So if they're off by a half wavelength, it's destructive interference. If they're off by full wavelength, it's constructive, but by half wavelength, it's destructive. And if that's off by half wavelength, then those 2 points are off by half wavelength, those two are off by half wavelength, and so all of them off, every point on here has another point which is off by half wavelength. And so you get a dark spot. So, if we think about the exact same math that we did with the double slit, we ended up with n lambda is equal to d sine theta. We're now producing dark spots, but we're off by a half wavelength, so we're off by half a wavelength is equal to d over 2 sine of theta. So for the first dark spot, so there's my very bright spot. This is very bright spot. Dark spot number 1. So they're off by a half wavelength instead of before it was off by a wavelength and it was a bright spot. Now we're off by a half wavelength and the 2's cancel out. And we're left with lambda is equal to d sine theta. The next bright spot, well, basically it's, you get pretty much the exact same formula. Nope, that's not what I wanted. And wait, 1 moment. And so the next one is when they are off by, well, if they're off by a full wavelength, then, yeah, there's a difference here between 2 things I'm seeing, so, sorry. Oh, okay, that's why there's an issue there, because I'm still looking at the wrong formula. And so it ends up where, yeah, we'll see. stick that in there. Same formula, this is just dark. And for single slit, and for double slit, this is bright. Let's see, that's not it. Oh, there it is. So this was where the bright spots were, the dark spots would be there, basically halfway between these and almost close to that one right there. Let's do it. Let's actually do the experiment properly. Let me grab the arrow.
You can have some line there falling out. You can have some line there falling out.
I think this is different hair.
Yeah, that's genetic.
Oh, it's easier. How does it make you feel?
Oh.
You're gonna fight your mom.
Alright, you kind enough to kill the lights? Sure. Alright, as you saw before, we have the bright spot here, you have a lot of little, tiny little dark lines. So you got the bright spot here, you can see where the double slit part is coming into it, but much easier to see that primary bright spot is there. So if I can draw that head on a little bit better, of the marker, that's that marker, there we go. So that's the brightest spot, make that a little bit bigger. The first dark spot happens here. Next dark spot there, dark spot, dark spot. All right, turn the lights on. The distance should still be about the same as it was before, which was 2.67 meters. This would be n equals 0. Actually, n equals 1, n equals 2, n equals -1, n equals -2, or whichever side you want to make positive, whichever side you want to make negative. I'm going to measure the distance between n is equal to -2 and 2 and divide by 2 just to get an average for that distance right there. Similar to the process I went through the last one. So the full distance, wow, about 7.8 centimeters. So for n equals 2, y would be 7.8 centimeters divided by 2, which is 3.9 centimeters, which is 0.039 meters. L, I'm assuming is still what, the same, 2.67 meters. And if we can assume that that angle is small, then we can use this version down here, that y over L is equal to the sine. And so I have 2 times my wavelength equals D, which is what we need to find, times y, 0.039 divided by 2.67. The wavelength is about 6.5 times 10 to the negative 7 meters. And so therefore, D, the width of the hair, is a D two. Anyone?
Calculator's out during the quiz. That'll teach me.
That was the issue. Like the opposite.
Is yours charged?
Yeah.
Why did you not charge?
There's no result.
8.9 times 10 to the negative fifth,
10 to the negative 6,
fifth,
fifth,
fifth power 5.
so about 89 microns.
Which we said human hair is about that.
Yeah. So it's not, I think last
It's
time
within
we
the
had,
range.
what were we last time?
Like what? 40s?
Yeah, there was a range though. It was
Yeah.
like, depending on the thickness of someone's hair.
I remember we were like 20.
I think we're,
the upper range.
yeah. I think we're at 40.
Alright, questions about single slit?
Did you find the
Oh, what?
range?
Oh, yeah, it's 1780 micrometers,
Yeah, I think we were at 150.
micrometers. Speak to me. This one.
Alright.
This
At
one's-
this point, we have enough, so Wednesday we'll do, a lab, I'll bring it in. But anyways, we'll have to- And hopefully by then, we'll have other color lasers as opposed to just the one color that we have here.
I have a green one.
You have a green laser? If you could bring that in on Wednesday, I'd appreciate that. Please, thank you.
Pretty blue one.
Try to
You have a blue one?
I don't have a blue one. Just
Is it-
green.
Well, I thought Aaron had one.
Depends on the,